Okay, so let's do more about bit strings. One special problem about bit strings is to find the number of so-called socially distanced bit strings. That means no two ones are sitting next to each other. So in a string, there is no one following another one. So no one in the string. So for example, if n equals to, so the length of the string is 3, we get 0, 0, 0, then 1, 0, 0, 0, 1, 0, 0, 0, 1, and 1, 0, 1. So no two ones are sitting next to each other. Let's make a preliminary discussion about the number of such socially distanced bit strings. So let's call xn is the number of socially distanced bit strings of length n. And length n socially distanced. So let's make a table here, n versus xn. For the first couple of values, if n equals to 0, x0 is 1, because empty string will do. So the empty string does not have a pair of ones sitting next to each other. So for n equals to 1, x1 equals to 2, of course. So 0 and 1 are both socially distanced. N equals to 2, x2 equals to 3. So because we have 0, 0, 0, 1, 1, 0. So these are all socially distanced bit strings of length 2. If n equals to 3, we have seen that x3 is 5, 0, 0, 0. A single one will be good anywhere. 1, 0, 0, 0, 1, 0, 0, 0, 1, and 1, 0, 1. Okay, so we got a series of preliminary results, but then we have to find a recurrence relation. X2 equals to 3, x3 equals to 5. Okay, and everybody will see already that the pattern is of a Fibonacci recursion. Every term of the sequence will sum of two previous terms here. 1 plus 2 is 3, 2 plus 2 is 5, and we expect 8 here and so on. Let's find a recursion for the number of such socially distanced bit strings of length n. Okay, so xn, let's pick up an element of xn, which is the bit string b1, b2, b3, all the way to bn. So these are all socially distanced bit strings of length n. There's two cases. Look at the first bit, very important, look at the first bit. If the first bit is 0, then we'll have a b2, b3, bn. So as long as b2, b3, bn is a socially distant bit string, everything will be fine. So how many strings are of this type? We have x up n minus 1, because we have n minus 1 bits, and the only condition that this bit string of length n minus 1 from b2 through bn must be socially distanced, which gives us x n minus 1. Or it is possible that the other case is the first bit is 1, in which case the second bit must be 0 because of the string being socially distanced. After 1 and 0, every choice will do. So we're going to put B3, B4, all the way through Bn, and the number of bit strings of length n that are socially distanced and begin with sequence 1 and 0 is x sub n minus 2. So in conclusion, xn, which is the number of socially distanced bit strings of length n, is xn minus 1 plus xn minus 2. So let's try to write down the recursion relation. Xn equals to xn minus 1 plus xn minus 2 for every n greater or equal to 2. Now we have a clear connection with the Fibonacci numbers. So the Fibonacci numbers are we have the same recurrence relation but different initial conditions. So let's get both of them, Fibonacci numbers and Xn, on the same table, n versus Fn versus Xn. So let's see. Okay, Fibonacci numbers are F0 is 0, F1 is 1, that's by definition. And then every Fibonacci number is the sum of two previous ones. So we get 1 here, 2 here, 3, 5, and put one more column. We get an 8, and so on. Okay, x0 we've seen it's a 1. x1, number of socially distanced bit strings of length 1 is 2. Socially distanced bit strings of length 2 is 3. Socially distanced bit strings of length 3 is 5. Then xn satisfy the same recurrence relation. We get an 8, we get a 13, we get a 21, and so on. So notice that we have an important shift. So x0 is can be matched with this one. X1 can be matched with this one. X3, so X1 will be matched with this one. X2 will be matched with F4. X3 will be matched with the F5. X4 will be matched with F6. X5 will be matched with F7. Here will be 13, and so on. So clearly, here the same recurrence relation, and the relation between the two sequences is a shift, which means xn equals to f sub n plus 2 for every n greater than or equal to 0. So that means we got a neat expression for the number of socially distanced bit strings of length n in terms of the Fibonacci numbers. Okay, so let's come back to bit strings and try to discuss other type of problems. So let's imagine like bit strings of length n in the form of a device. We need to have n cells. Each cell hosts a bit, which is a 0 or a 1. So let's say the bit hosted by the first cell is B1, then B2, B3, and so on until Bn. So it's like a physical system in which has to the power n states, because every cell can be in one of the two states. So 2 states per cell, and the choices of the states per cell are independent of each other. So if 2 to the power n global states of this device. Okay, so one interpretation, a nice interpretation of binomial coefficients is n choose k is the number of states with k ones. So number of bit strings of length n with k ones. So on this system, let's assume that the states of the system are equally probable. So the probability of every state being to the power n global state, probability for every state b1, b2 through bn of this string is 1 over 2 to the power n. Okay, so this being said, let's calculate by using binomial coefficients the following. The expected value of the random variable, which is defined as the sum of the bits. So let's define the random variable x, which will be summation from I equals to 1 up to n of bi. And we need to calculate the following quantities: the expectation of x and the variance of x, by applying binomial coefficients and their identities. Okay, so let's try to start. Again, these strings are b1, b2, let's put them here. X equals to b1 plus b2 plus bn. Well, the expected value of x equals to the total number of states of the device is the total number of these strings of length n is 2 to the power n. So 1 over 2 to the power n, let us put as a factory in the front of the sum. Summation over all possibilities for the number of ones. Number of ones could range from 0 to n. The variable x, if we have k ones, is k. And the number of states where the random variable x takes the value k is n choose k. So 1 over 2 to the power n, which is the probability of every bit string, and summation from k equals to 0 up to n. The value of the random variable k is realized for n choose k states. So let's try to calculate this sum. Let's first prove the lemma. It's a preliminary result. K times n choose k equals to n times n minus 1 choose k minus 1. For every k, for every k is bigger than or equal to 0, right? If k equals to 0, because of this k, we'll get left hand side is 0, and the right hand side, because k is 0, every binomial coefficient with a negative number at the bottom is still 0. So, okay, so let's try to move this stuff. So this would be k times n factorial divided by k factorial n minus k factorial is n times n minus 1 factorial over k minus 1 factorial times n minus 1 minus k minus 1, which would be still n minus k factorial. And that will mean, well, k with k factorial is simplified, we get a k minus 1 factorial at the bottom. n minus k factorial with n minus k factorial will go. N with n minus 1 factorial, they go together, we get an n factorial. N factorial with n factorial, they simplify. K minus 1 factorial with k minus 1 factorial, they simplify, and we are left with 1 equals to 1, which means we validated the identity. Okay, so using this identity, so let's try to come back to our sum. The expected value of x is 1 over 2 to the power n, summation from, we can put as well k equals to 1 up to n, because the term k equals to 0 does not leave anything in the summation, does not contribute to the summation. K times n choose k equals to summation 1 over 2 to the power n, summation from k equals to 1 up to n. Let's use the identity we just proved. N times k minus 1 is k minus 1. Okay, now the sum is over k. So that means we can take all the entities that do not depend on k in front of the sum. So this equals n over 2 to the power n and summation from k equals to 1 up to n minus 1 of n minus 1 choose k minus 1. And this is the sum of all binomial coefficients of n minus 1. So n minus 1 choose 0, k starts from 1, plus n minus 1 choose 1, all the way through n minus 1 choose, still n here. n minus 1 choose n minus 1. The sum of all binomial coefficients is 2 to the power n minus 1. So we got to this point where this is n over 2 to the power n and 2 to the power n minus 1. And simplify 2 to the power n to the power n minus 1 equals to n over 2. So in a randomly selected bit string of length n, the expected value of the random variable sum of the bits is n over 2. So in other words, we expect n over 2 watts. Okay, so let's write down the result. Expected value of x is n over 2. Okay, let's move further. The variance of x is expectation of x squared minus expectation of x everything squared, which is expectation of x squared. Then the square of the number of ones in a randomly selected bit string minus the expectation of x squared, so minus n squared over 4. We just calculated p of x. So in the remaining part of this problem, we'll calculate the expectation of x squared. So p of x squared equals to 1 over 2 to the power n summation from k equals to 0 up to n k squared times n choose k. Because there are n choose k bit strings of length n, which have k ones, so for which the square of the random variable x squared is k squared. Okay, so how to do this problem? So, as before, we can just as well start from k equals to 1 to n. So it's 1 over 2 to the power n, summation over k equals to 1 up to n, k squared times n choose k. And there is a tricky thing here. So if you look at n choose k, write it in terms of factorial, at the bottom we have k factorial. K factorial does not simplify as well as with k squared. It is better, we rather have k times k minus 1 instead of k squared, so that we can simplify with the last two items in k factorial, which are k minus 1. Therefore, we artificially subtract and add 1. So that I get our k times k minus 1. So what we do, in other words, 1 over 2 to the power n times summation from k equals to 1 up to n, k squared minus k plus k times n choose k, and split the sum into two sums, first by considering this k minus k, and second by considering only this k. So this will be 1 over 2 to the power n, summation from k equals to 1 up to n. K squared minus k, which is k times k minus 1, times n choose k, plus, let me put a bracket here in front of it, plus summation from k equals to 1 up to n, k times n choose k. Close the bracket. Okay, so we have to calculate this one. So let's try to erase the work and the fruit of the work. So E of x squared will be, turns out to be this. Let me copy it here once again, 1 over to the power n, summation from k equals to 1 up to n, k times k minus 1, n choose k. By the way, if k equals to 1, still this is a 0, so we can just as well start with summation from 2. So k, summation from k equals to 2 up to n, k equals to 2 up to n, k times k minus 1, n choose k, plus this summation from k equals to 1 up to n, k times n choose k, we calculated before we did the expectation of x. That was n times to the power n minus 1. Okay. Okay, so now, before going further, let's try to write down another combinatorial identity between simplifying k times k minus 1 times n choose k. Previously, I gave you a analytic formula. Now, let's try to prove a combinatorial formula about the term k times k minus 1 times n choose k. And the identity is k times k minus 1 times n choose k equals to n times n minus 1 times n minus 2 choose k minus 2. Okay, so here is the idea here. We have n objects, n persons, and out of n persons, let's try to select a team of k together with a president and vice president, like two distinguished elements, but one of them is on a different footing than the other. So in the selected k elements, one of them is the president, so to say, another one is VP. A P and a VP. In how many ways can we select k out of n? In n choose k once. So basically, we first select the team of k, and then within that team, we select the president in k ways. And after we select the president, we select the vice president in k minus 1 ways. So that's the left-hand side counts the number of ways of selecting the team of k persons out of n. And within that team of k persons, we got a president and vice president identified. The second alternative, let's look at the right-hand side. Again, we have n persons. And then we do the team first. First, we select our president and vice president, P here and VP here. After selecting the president and the vice president, we have to complete up to a team of k. So we have to select k minus 2 more. Right? Out of how many? The president and the vice president have already been selected, and therefore the k minus 2 remaining number of members of the team will be selected out of n minus 2 elements. So, selecting vice president followed by a vice president can be done in n times n minus 1 ways. After we selected the P and the VP, the remaining k minus 2 members will be selected out of the remaining n minus 2 members in n minus 2 choose k minus 2 ways. So, there are two different ways of counting the same structural combinatorial function. So, it's a very important formula. So, k times k minus 1 times n choose k is n times n minus 1 times n minus 2 choose k minus 2. Obviously, this can be extended if you want to go further. One step, k times k minus 1 times k minus 2 times n choose k. By the same logic can be written as n times n minus 1 times n minus 2 times n minus 3 choose k minus 3, etc. So that's very important. In this case, we choose a team of k out of n. Within that team, we'll select the president, vice president, secretary. Or we choose the president, vice president, secretary first out of n, and then from the remaining, we compete with k minus 3 members of the up to the team of k. Okay, this being said, let's go back to our calculation of the expected value of x squared by using this combinatorial identity. So let's continue here. Equals to 1 over 2 to the power n times summation from k equals to 2 up to n times n minus 1, n minus 2, choose k minus 2, plus n times to the power n minus 1. This will be this first sum, so n times n minus 1 can be put in front of the sum, and we are left with summation from k equals to 2 up to n minus 2 choose k minus 2, and overall we get n times n minus 1, which is in front, times summation from 2 to n minus 2 choose k minus 2, but k minus 2 varies from 0 all the way through n minus 2. So all combinations of n minus 2, choose 0, choose 1, choose 2, up to choose n minus 2. So n times n minus 1 times n minus times 2 to the power n minus 2. So this will be 1 over 2 to the power n times n times n minus 1 times 2 to the power n minus 2 plus n times 2 to the power n minus 1. Okay, so let's see what it is. Expected value of x squared 1 over 2 to the power n times. We can pull out 2 to the power n minus 2 common factor times n minus 1 plus putting the factor of 2 to the power n minus 2 gives us an extra factor of 2 from here plus 2n then. And that will be 1 over 2 to the power n times 2 to the power n minus 2 times n squared plus n, which is n times n plus 1. And that will be n times n plus 1 over 4. Okay, so e of x squared is n times n plus 1 over 4. And then the conclusion of the variance of x, that means the variance of a random variable, sum of the number of ones in a randomly selected d strings of length n. This string of length n is e of x squared minus e of x squared equals to n times n plus 1 over 4 minus n squared over 4, which will be n squared over 4 plus n over 4 minus n squared over 4 is n over 4. And that's the final objective in this problem.